Welcome everybody. Thanks for tuning in again. Today we're going to talk about how do you make the nuclear material that are needed for making a nuclear bomb. In the last talk I talked about how you need plutonium or highly enriched uranium are the materials that are used in the nuclear weapons that exist today, although there are some other isotopes that conceivably could be used to make nuclear weapons. So there are two paths to the bomb, the plutonium route and the uranium route. On the plutonium route, you need a reactor. You put uranium fuel into that nuclear reactor. In that reactor, the reaction is taking place and releasing neutrons. The uranium fuel absorbs neutrons. Some of it turns into plutonium. Okay? Then you have to take that spent fuel, as it's called, out of the reactor, and you have to chemically separate out the plutonium that you want from all of the uranium and the fission products, which are very radioactive, and you don't want them in the stuff that you're handling for your nuclear bomb. So you need a reactor and you need a reprocessing plant that does that chemical separation. On the highly enriched uranium route, you need an enrichment plant. That is something that takes these almost identical atoms of uranium-235 and uranium-238 and separates them out. Okay? Let me talk for a moment about what uranium-235 and 238 are and a little bit of the physics here. So an element is a kind of material characterized by how many protons it has in its atomic nucleus. So hydrogen has 1, helium has 2, uranium has 92, plutonium has 94. Okay? Now, different kinds of an element can have different numbers of neutrons. So last time when we were talking about fusion thermonuclear weapons, I talked about deuterium, which is hydrogen with a neutron along with the proton in its nucleus. So it has a dual nucleus, 1 unit of proton and 1 unit of neutron. And I talked about tritium, so 3 things in the nucleus. The proton, because always 1 proton defines that it's hydrogen, plus 2 neutrons makes 3 for tritium. Okay? So uranium-235 is an isotope of uranium that has 92 protons, and the rest, adding up to 235, are neutrons. So neutrons plus protons gives you the isotope number, like uranium-235. Okay? Uranium-238 has 3 more neutrons. Okay? Those 3 extra neutrons make uranium-238 very difficult to split and incapable of sustaining a nuclear chain reaction, either a chain reaction in a reactor or an explosive chain reaction in a bomb. So you need the uranium-235 to get that chain reaction going. So the uranium that you dig up out of the ground includes less than 1% of the uranium-235. It includes 0.7% uranium-235. All the rest, almost all the rest, is uranium-238. Okay? So how do I separate out the teeny amount of uranium-235 from that huge amount of uranium-238? Well, there's several techniques, and I'll talk about them today. There's gaseous diffusion, centrifuges, laser. Now, as I mentioned last time, none of these materials occur in nature. All of them are very difficult to produce. And one thing to remember, in some past years, some students have used the terms reprocessing and enrichment interchangeably as though they're the same thing. They're not. Reprocessing is on the plutonium route. It's a chemical process. Enrichment is on the uranium route. It's usually not a chemical process. It's usually a physical process based on the mass of these different isotopes being slightly different. Okay, so reprocessing is not equal to enrichment. All right, so this is just another version of these two paths to the bomb. They both start with natural uranium. You've got to dig it up out of the ground, mill it, and get it ready. Okay? On one path, on the uranium path, you send that to an enrichment plant. And you might end up with your product, if you're making bomb material, being something like 90% uranium-235, as opposed to 0.7% that you started with, and 10% still uranium-238. Whereas your waste, which are referred to as the tails from enrichment, might be, for example, 0.2% U-235, rather than the 0.7% you started with. Takes up a lot of energy to get all of the U-235 out. So the tails usually have a fair amount. Might be 0.2%, might be 0.3%, might be 0.4%, somewhere in that range. And the rest, uranium-238. Okay? On the plutonium route, you have the reactor. In the reactor, the uranium absorbs neutrons, some of it turns into plutonium. You have the spent fuel that has about 1% plutonium, and then the other 99% is the uranium and the fission products. Okay? How much is the fission products depends on how long that spent fuel has been in the reactor, how much power it's generated, how much fission has taken place. Okay, so then you do the reprocessing, and that separates that spent fuel into three heaps. A heap of plutonium, a heap of uranium, and a heap of high-level waste, which is where the fission products go. Okay? So both routes start from mining uranium. Both end with converting the products, either the uranium or the plutonium, to metal, and then from that metal, making bomb components. These are just some pictures to help you with that same way of thinking. So you start with mining. You see a picture there of a uranium-bearing rock. Now, when you dig it up out of the ground, it's literally a rock, and the rock contains some uranium, but it's mostly rock. So you need to do what's called milling to get purified uranium from those rocks. And usually you end up with a particular oxide of uranium that's U3O8, which is referred to as yellow cake. So you can see the picture under milling there is a bright yellow powder. That's why it's referred to as yellow cake. Okay? So then if you're going the enrichment route, you need to figure out a way to take that uranium, which is a solid when it's in the yellow cake form, and make it into a gas. Because almost all of the enrichment techniques that people have thought of involve a gas going through a process. Okay? Now it turns out, more or less by accident, that the only chemical compound of uranium that is a gas at reasonable temperatures and pressures is uranium hexafluoride, that is UF6. So one uranium atom, 6 fluorine atoms. Now, any of you who know very much chemistry can probably guess that anything with 6 fluorines in it is going to be a nasty toxic substance, and that is certainly true of uranium hexafluoride. All right, so you take uranium hexafluoride. I have a picture of one of the huge barrels that's stored in here, and that goes to an enrichment plant. We'll talk more about enrichment later, but that separates out the slightly lighter uranium-235 atoms from the slightly heavier uranium-238 atoms. And then you go to conversion to metal and fabrication. You can see there a ring of, I believe it's plutonium metal in that picture. Now on the lower route, which is the plutonium route, you take that yellow cake that you got from milling the uranium that you mined, and you convert it to some different thing. You might convert it to metal, or you might convert it to oxide, depending on what kind of fuel you're using in your reactor. So then you fabricate it into fuel. You put that fuel into the reactor. It sits in the reactor for a while, generates some fission. You end up with plutonium in the spent fuel. You take the spent fuel, and after storing it in a pool for a while to let it cool off a little bit, you send it to the reprocessing plant, which chemically separates out the plutonium, and then you send it to the conversion and metal fabrication stage. So this is just a picture of the civilian fuel cycle, which gives you a feel for the scale. So you start off with 170 tons of uranium as uranium oxide on the left side of the picture. That's coming from your milling plant after your mining. And you end up with only 24 tons of fuel actually going into the reactor, and then which is on the right side. And then, as I mentioned, after it's been in the reactor for a while, you put it in literally a swimming pool of water, and of course you don't do a whole lot of swimming in that particular pool, and you let it cool for a while, and then you can either reprocess it. You can do that for civilian purposes as well, to get plutonium that you would then use as civilian reactor fuel instead of bomb material, or the reprocessing can also provide bomb material. This is one of the basic problems of the nuclear age, is that the enrichment that's needed to produce highly enriched uranium is also needed to produce low enriched uranium for civilian power. And it's more or less similar technologies that can do either bombs or fuel for civilian power plants. And similarly, the reprocessing that some countries use to treat spent fuel can then provide either plutonium for civilian fuel or plutonium for nuclear weapons. All right, so it turns out that all of the ways that humans have thought of so far to enrich uranium only do a little bit of enrichment at a time. So it concentrates the uranium-235 a little bit more than it used to be concentrated. So you have to hook a whole bunch of them together in what's called a cascade. So you have lots of separating units, whatever technology of separating unit you've got, and you put the feed in more or less in the middle of the cascade, and then the stuff that is a little bit more enriched goes toward the product end of the cascade and gets more and more and more enriched at each stage. And at each stage, the stuff that's a little bit less enriched gets fed back to the previous stage, so that you can strip more of the stuff out. These cascades can be fairly complicated to model and certainly complicated to build and operate. But the basic notion is you've got a flow of more and more enriched stuff heading toward the product, and a flow of less and less and less enriched stuff becoming tails heading toward the tails end of the cascade. So if you want to make highly enriched uranium, you need a lot of stages where you have smaller and smaller numbers of separating units at each of those stages as you get toward more and more enriched material. So you would put the feed in at the largest of those green bars, and then as you get toward the smaller and smaller and smaller number of machines at each stage, you're getting to the more and more and more enriched material. And then the stuff toward the left of the tallest green bar is where you're stripping out the U-235 from the tails. And then that relatively small green bar at the far left is where the tails would eventually come out of the cascade. Now, if you weren't going to enrich it as much, if you only wanted to produce low enriched uranium, you wouldn't need as many stages in your cascade. All right, so one way that you can set up these cascades, one technology that you can use, is called gaseous diffusion. And so what this is you put in a gas, uranium hexafluoride, at fairly high pressure, and you have a barrier that has tiny microscopic holes in it. Okay? And these atoms are bouncing around in the gas, and the uranium-235 atoms, because they're lighter, for the same amount of energy, bounce a little bit faster. So in order to have the same kinetic energy with less mass, they got to go a teeny bit faster. And so there's a slightly higher chance that one of those atoms will find one of the holes in the barrier material and pass through to the other side of the barrier. Okay? But it's only a slightly different chance, very slightly different chance. So you need to have another barrier and another gaseous diffusion unit and another barrier and another gaseous diffusion unit and so on and so on and so on. And in fact, you need gigantic facilities. The facility in the picture there is one of the US enrichment plants that's since been dismantled. It was absolutely huge. I mean, they used bicycles to go up and down the enrichment halls because it was just too far to walk to get there at any reasonable amount of time. And this process, because you're putting this stuff in at high pressure, you need these big pumps to get it to go through. It requires a huge amount of electricity, a giant amount of electricity. It is essentially a process of turning electricity into enrichment. And electricity is overwhelmingly the major cost that you have when you're operating one of these gaseous diffusion plants. In the United States, we still have a gaseous diffusion plant. Well, we're in process of shutting down the last gaseous diffusion plant, as is France, but we've been the last country still operating big gaseous diffusion plants in the world. And they're in the process of replacing them with centrifuges, which I'll talk about now, which are much more efficient. So in a centrifuge, what happens, these now dominate world enrichments, partly because they are just dramatically more efficient. Factor of 20 or more reduction in the amount of power required. So what's happening in a centrifuge is that you have a tube which is spinning. I'll get to that in a moment, actually, when I have the picture. Let me talk about what's on this slide first. So the technology of centrifuges is problematic from the point of view of nuclear weapons proliferation because, since they're so much more efficient, they're small and easy to hide. A plant to produce enough bomb material for a bomb each year, one bomb a year, would fit easily on this floor of this building and would use less power than a typical supermarket. So there's a lot of buildings in any country that could easily be a centrifuge plant, for all you know, when you're looking at it from, for example, a satellite photograph. So it's a problematic technology in that respect. It is technologically demanding, although, as I'll mention, there are debates as to how technologically demanding it is. The black market network led by Pakistan's Abdul Qadir Khan was marketing centrifuge technology, which is really the technology of choice for the determined nuclear cheater, to countries all over the world. They sold them to Libya, they sold them to North Korea, they sold them to Iran. They also provided, at least to Libya, a bomb design and possibly to their other clients. They attempted to sell centrifuges to Saddam Hussein's Iraq. They didn't have a chance to take them up on the offer before the 1991 war intervened. North Korea now has a centrifuge plant. We don't know yet whether they are making HEU there or not, and whether they have another plant that they haven't shown the outside world or not. All right, so let's get back to what a centrifuge is and how it works. The basic idea is to spin a tube with this uranium hexafluoride gas in it at very high speeds. And then, because the slightly heavier atoms, it's harder to deflect their course than it is with the slightly lighter atoms. The slightly heavier atoms end up getting flung against the outer wall of the tube, and the area toward the center of the tube ends up being slightly enriched with the lighter atoms. Now, because designers are clever, they figured out, a guy named Gernot Zippe in particular figured out that if you add a flow going up and down to the spinning action, you can actually make the whole system much more efficient. So you have this flow going up and down in the centrifuge that is caused by certain baffles and so on that you put in the rotating thing. And so you take the product out from the middle and the tails out from a little bit further away from the middle. Now, what is hard about making a centrifuge? Well, first of all, you need really strong and yet lightweight material, because this thing is spinning at incredible speed, and you have, it's experiencing accelerations thousands of times the acceleration of gravity. And so if it's not very, very strong, it's going to tear itself apart. In the early days of the US program, I'm told that the workers referred to the centrifuges as explosive self-disassembly machines, because when they got unbalanced, they would tear themselves apart, and chunks of metal would literally go flying around the room at something like the speed of sound. So one of the things that they have developed since then is putting casings around the spinning tube so that if the spinning tube does fail, the chunks aren't going flying around the room. All right. So you need very strong material, and you need a really great bearing so that this thing can keep, which is fairly heavy, can keep spinning for a long, long time. And there are different kinds of bearings that people have developed over the years. A lot of the specifics of how the bearings work remain classified. Originally, it was they were resting on basically a piece of piano wire, but as you might imagine, that didn't work too awfully well. So there are, for example, ball bearings with tiny grooves cut in particular ways in them to allow certain kinds of oil to go in there and keep the thing lubricated. Or there are magnetic bearings where the whole thing is just floating in a magnetic field. The magnetic bearings are usually used for the top of the centrifuge, but in some advanced centrifuges they're also used on the bottom. These are, this is then President Ahmadinejad of Iran visiting the centrifuges in Natanz. You can see they're sort of, it's almost like an experimental facility in that they're hooked together in a very complicated way to create this cascade flow of uranium hexafluoride there. This is a more standard sort of cascade, but in order to do it, you need lots of centrifuges together to get substantial enrichment going, as I mentioned. Now, one important thing to understand is enrichment is a very nonlinear process. Once it gets going a little, it accelerates and accelerates and accelerates. So when you have gone from the 0.7% U-235 that you dig up out of the ground up to 4.5% for a civilian power reactor, you have already done 3/4 of the work of going all the way to 90%. So that's why the international community is so concerned about Iran building up these stockpiles, some of which are at 4.5% or so, some of which are at 20% or so. They're far from 90% in the actual percentage, but in terms of the amount of the enrichment work that's already done, it's a huge fraction. Once you get to the 20% enrichment level, you've already done about 90% of the work of going to 90% enrichment. So that means if you have a stock of that kind of stuff, then it's much easier to have a small number of centrifuges somewhere secret and do the final enrichment up to 90% with that smaller number of centrifuges. And we'll talk about that later in the class. So one obvious question is, well, how difficult is it to do enrichment? And in particular, to do these centrifuges that are relatively small and easy to hide. And there are differing views on this difficulty, and there's differing evidence to support those differing views. So Iran, for example, which has, other than Israel, the most advanced indigenous science and technology base in the Middle East, probably, had complete centrifuge designs way back in 1987. And it took them something like 20 years to get a functioning cascade actually enriching uranium, despite that. So building those kinds of centrifuges requires hard-to-get specialty materials. So remember I said you needed these very strong and yet lightweight materials. So you will often see references to a particular type of steel called maraging steel. This is a type of steel that is actually quite difficult to produce, and there's only a few companies that make maraging steel, and that's used in some centrifuges. Also, these days, carbon fiber is used in centrifuges, but again, carbon fiber of the requisite quality is often not easy to get or easy to make. They also require exquisite balancing. If the centrifuge is even a teeny bit heavier on one side than another, when it's spinning at these very high speeds, it will tear itself apart. So when the centrifuges from the AQCon network were discovered in Libya, for example, a colleague that I was speaking to at the International Atomic Energy Agency, who's a centrifuge expert, was shown the centrifuge rotors that they were going to use for these centrifuges. And he told me the first thing I did was I took my bare hand and I grabbed each of the rotors, because there's enough oil on my hand just naturally that no matter how much you cleaned those rotors after that, you'd never be able to use them for centrifuges again. So they require exquisite balancing. The bottom bearing, as I mentioned, is often difficult to make for this type of centrifuge. And a number of countries have been working on that kind of centrifuge. But on the other hand, you also have a number of countries who have developed relatively simple centrifuges with a relatively small number of people in a relatively small amount of time. So there are people who argue we shouldn't be spending so much time trying to restrict the technology of centrifuges, because countries, if they do it properly, can develop them themselves without requiring all of this specialty stuff. Now, as I mentioned, centrifuge plants can be fairly easy to hide. They take up relatively little space and little power. The plant to make enough HEU, as I mentioned, would, for a bomb every year, would fit in this building. The leakage of uranium, yes, leaks a little bit of uranium, but it's fairly modest, partly because the pressure inside a centrifuge is actually less than the atmospheric pressure outside. So if there's a little bit of a leak, it's the air going in rather than the uranium hexafluoride coming out from the centrifuge. So how to find them is an interesting problem. Some years ago, the US intelligence community had a big meeting to talk about all the different ways people were thinking about how would you detect centrifuges? Could you hear the hum of the spinning centrifuges from some distance away? Would the signal of the spinning get back into the electrical system, and could you detect that coming over the wires of certain frequencies and so on? And a colleague of mine was given the job of being the rapporteur for this meeting and going around to the individual groups that were working on different kinds of things. And it was all a very classified meeting, of course, but his summary of the situation was, nobody has a good idea. All right, so this is a picture of the North Korean centrifuge plant, which nobody knew was there until the North Koreans decided to bring a former US nuclear lab director, Siegfried Hecker, to visit it. So until they decided to tell us it was there, we didn't know it was there. It's in a building that used to be a fuel fab building, The only thing unusual about that building is they put a fancy blue roof on it. It's almost as though they were trying to tell the Americans, look at this building, something interesting is happening here. And what's happening in this picture is it appears that they are in process of doubling the size of this centrifuge operation. They're basically building an identical size thing next to the original building. This is a picture from a few months ago, and now there's an identical blue roof on over that area next to this building. All right, so let's talk about producing plutonium for a minute. All right, so you irradiate uranium in a nuclear reactor, as I said. U-238 absorbs neutrons, and it becomes plutonium. And then you reprocess the spent fuel to get the plutonium out from the other thing. So what does reprocessing involve? Well, in the main technique that was originally developed during World War II and has been used since then, you chop the spent fuel into little pieces. The pieces get dumped into boiling nitric acid to dissolve the uranium and plutonium and fission products. And then you take that nitric acid and you contact it with some organic material. These days they use an organic solvent called tributyl phosphate. And if you do certain chemical steps, you can pull the plutonium into the tributyl phosphate, into the solvent, and leave the rest in the acid. So, and then typically you separate, at the same time you separate the uranium from the fission products as well. So as I mentioned before, you have really three piles: a pile of plutonium, a pile of uranium, and a pile of fission products resulting from the reprocessing. And this typically, both the reactors and the reprocessing plants are typically, though not always, large and observable facilities. So this photograph here is a photograph that a Senate staffer took of on a visit to the North Korean nuclear reactor that has produced the plutonium that North Korea has so far, which was the focus of the first phase of the North Korean nuclear crisis in 1994. This is a schematic of that reactor. You have a fuel handling machine at the top. The reactor itself is basically a big pile of graphite reflector blocks, and you have these tubes of fuel that go down into the reactor core, and a concrete shield around the outside of the whole thing. This is the North Korean reprocessing plant at the same site at Yongbyon. You can see it's a fairly observable facility. One thing, if you look closely, you will see a tall tower with a long shadow. That is the stack for releasing some of the gases from reprocessing. That's fairly characteristic of a reprocessing plant. Usually these are fairly detectable facilities, but again, if you think hard about it, you might be able to do reprocessing in smaller places that would be less detectable. All right, so one key question is, how close a connection is there between civilian nuclear power and the military use of nuclear energy, between power plants and bombs? So again, enrichment and reprocessing are really the key technologies that pose serious proliferation risks. If you don't have enrichment, you don't have reprocessing, you can't really make the material you need for a nuclear bomb. If you do have a plant for either of those purposes in your country, then you're in a certain sense a decision away from being able to make nuclear bomb material. You could use those plants anytime you wanted to make nuclear bomb material. Now, some people, I think a lot of people assume when they're first learning about this topic, oh, but surely to make a nuclear bomb, I must need a bigger, more complex, fancier plant than just to make, the relatively low-grade material I need for a nuclear power plant. Unfortunately, exactly the opposite is true. You need a much bigger and nicer plant to do enrichment for civilian purposes or reprocessing for civilian purposes, because you need to actually be able to make money out of it, so it has to be efficient and so on, than you need for nuclear bomb purposes. And one key element of that is just the scale. So remember, when you're making 3, 4, 5% material for a nuclear power plant, you've already done 3/4 of the work of going all the way to 90%. But you need a lot of material for that nuclear power plant. You might have 30 tons of that 4 or 5% enriched material in the core of a nuclear power plant. Whereas, remember, the Hiroshima bomb, which is a very inefficient bomb that used a lot of material as nuclear bombs go, was only 60 kilograms. And an implosion type bomb might be only 15, 20 kilograms. So the official IAEA significant quantity numbers are 25 kilograms of U-235 contained in highly enriched uranium, or 8 kilograms of plutonium. So we know, given that the Nagasaki bomb was about 6 kilograms of plutonium, and that, as we talked about, implosion devices have been developed that are more efficient than that original solid core device, that bombs can be made with less than the IAEA significant quantity number. But the IAEA number is designed to refer to not only the amount that actually goes into the bomb, but also the amount you would need counting wastage and the various scrap and so on that you'd end up with, and to refer to the relatively crude bomb that a country might make for their first one. There is a lot of controversy, even so, over whether those IAEA numbers should be reduced. In any case, the key technologies you need to worry about with respect to nuclear proliferation and the intersection with civilian nuclear power are enrichment and reprocessing. So if a country builds a nuclear reactor and doesn't build enrichment and reprocessing, then it does not help it much in getting closer to the bomb. It does help. Certainly the reactor produces plutonium in the spent fuel, but if you haven't got a reprocessing plant to get at that plutonium, then you can't use it to make a bomb. The reactors, civilian reactors, are typically under International Atomic Energy Agency safeguards. They're all under IAEA safeguards unless they're in states that already have nuclear weapons. So removing that material to separate out the plutonium would be detected. Okay? The fresh fuel in the reactor is this low enriched material that can't be used in nuclear weapons. It can sustain a chain reaction in a reactor, but it can't sustain an explosively growing chain reaction. Okay? The spent fuel does contain plutonium, as I mentioned, but it would take reprocessing to get it out. But at the same time, civilian reactors provide a base of trained people who understand nuclear reactions, and it may give you the opportunity to build up contacts with other countries, for example, the country selling you the reactor and helping you build it, which may lead to more sensitive transfers. So for example, in the 1990s, when Russia first contracted with Iran to build a nuclear reactor at Bushehr, actually to finish off one the West Germans had started before the Iranian Revolution, the United States tried to convince Russia not to go ahead with that contract. And we were concerned about that contract not because the US government thought that plutonium for an Iranian nuclear bomb was going to be made in Bushehr, but rather because hundreds of Iranians were coming to Russia and training at various nuclear institutes in Russia and making the personal contacts that might help them get other technologies. As it turns out, they were already getting the technologies that we were most worried about, centrifuge technology, from the AQCON network and not from Russia. So part of my career in the 1990s ended up being wasted trying to stop something that was already happening through another channel. So they provide a base of personnel, possibly a set of contacts. They provide a justification for pursuing enrichment or reprocessing whose military purpose would otherwise be obvious. So Iran, for example, argues our enrichment program is entirely peaceful. We're only making fuel for our power plant and fuel for our research reactor. We don't understand why everyone is so worried about what we're doing. Finally, a nuclear power program provides a bureaucratic power base involving, control of billions of dollars, large organizational infrastructure, and so on, for nuclear advocates who, in many cases, may also end up advocating for nuclear weapons. There are also opposite cases where the nuclear power industry, partly to maintain its supply from foreign countries, has argued against a nuclear weapons program in particular countries. So these issues are at the heart of several current controversies about nuclear proliferation and nuclear power. As I mentioned, Iran says its enrichment is purely for peaceful purposes and completely legitimate. South Korea, at the moment, is in a situation where it's right across the border from North Korea, which already has nuclear weapons. Something like 2/3 of the people in South Korea think South Korea should develop nuclear weapons. And South Korea is asking the United States, in the negotiation of a new civil nuclear cooperation agreement, to give it prior approval to go ahead with enrichment and reprocessing of US origin nuclear material. And the United States is reluctant, fearing that that might increase the proliferation risk in South Korea, that it might make it impossible to convince North Korea to stop doing those things, or that it might make it more difficult to convince other countries beyond South Korea not to establish their own enrichment and reprocessing capabilities. Similarly, there's a significant controversy in the US government over what is sometimes referred to as the gold standard for civil nuclear cooperation. So the United Arab Emirates, some years ago, signed a civil nuclear cooperation agreement with the United States that explicitly prohibited the United Arab Emirates from building enrichment or reprocessing facilities. And some people say, well, we ought to have that requirement in all of our civil nuclear cooperation agreements. That ought to be the standard that we insist on. But a variety of other countries say, I don't want to give up my rights. I have every right, if I want at some point in the future, to build an enrichment plant or a reprocessing plant to support my civil nuclear program. Japan has both enrichment and reprocessing. Well, I don't see why I should give up my right to be able to do this. Not that I want to do it right now, but I don't want to negotiate away my rights. So other people say we shouldn't insist on an explicit agreement to ban enrichment and reprocessing, because if we do, other nuclear suppliers that don't insist on that will come in and sell their reactors, and we'll have even less proliferation controls than we would if the United States entered into civil nuclear cooperation agreements without such an explicit ban. Similarly, there is a group of the major countries that export nuclear reactors or nuclear materials, which is called the Nuclear Suppliers Group. And they've just agreed on a new set of criteria that says basically we will not export enrichment and reprocessing technology to a state that doesn't already have it unless the state meets this set of criteria we've now agreed to. And we'll have more on the link between civil nuclear power and proliferation later in the class. So again, just to recap, 2 paths to the bomb: the plutonium route, the uranium route. The plutonium route involves a reactor. The uranium absorbs neutrons in the reactor. Some of it turns into plutonium. You take it out of the reactor, then it's called spent fuel. You chemically process it, a process called reprocessing, separates out the plutonium. On the uranium route, you take the uranium that you mined, you convert it to uranium hexafluoride, you put it into an enrichment plant, that separates the uranium-235 from the uranium-238, and you end up with the weapon-grade uranium that you want for your nuclear bomb. Thanks very much.